Hello everyone, welcome. Thank you so much for joining today's USACM student chapter online seminars. It is my great pleasure to introduce today's speaker, Noe Reyes Rivas. Noe was born and raised in New York City and earned his bachelor degree in mathematics from Andrews University in 2023. He is currently a third-year Ph.D. student at Brown University, where he works in applied mathematics. His research focuses on numerical methods for partial differential equations under the guidance of Professor Braden Case. Beyond his research, Noe is also a longtime piano player. He has been playing piano for over a decade, and he's particularly into jazz. So if anyone here wants to talk about music later, you may have a great conversation with him. He's also really interested in philosophical discussions and reasonings, which I think may be complementary to thinking deeply about math and PDEs. We are very happy to have Noe with us today to share his work and perspective. Thank you again for being here, Noe. The screen is yours. I will mute myself.
Thank you so much for the introduction. It's truly an honor to present in the student chapter. And so without further ado, I guess we can get right into it. So the the title of my talk is Contact Express, a New Approach for Contact Problems. This research was done also in part with my advisor, Brendan Keefe. So let's get into it. Here we go. So I want to give a quick outline of the talk. So to gain an appreciation of the math that we'll be discussing later, I'll start by introducing Legendre functions and Bregman divergences. From there, we'll talk about the Bregman proximal point method, which is an optimization algorithm. And then we'll get into really the main topic of this talk, which is Signorini's problem. And we'll talk about how our algorithm contact express is related to this other algorithm called proximal Galerkin. Lastly, we'll dive into some numerical results in the end. So let's start by talking about Legendre functions. So we say that a function R, which is proper convex and lower semi-continuous, is a Legendre function if it satisfies these properties. So this first one says that the interior of its effective domain, that is the set of points where it's not infinite, it is not empty. We assume that R is differentiable and strictly convex on the interior of its effective domain. And this last property is known as essential smoothness, which states that if you have a sequence in the interior that's approaching a boundary value, then the magnitude of the gradient evaluated at that sequence blows up. And I also want to comment on what these terms mean. So proper essentially means that our function R is not identically infinity, that at some point it takes like a finite value. And then this lower semi-continuous, it's not strictly necessary for our purposes, like the definition, but you can think of it as a weaker notion of continuity. So I want to present some examples of Legendre functions. So here we have a whole family of Legendre functions where this P is a strictly positive power. In particular, you notice that if you take P equals 2, then a quadratic is a Legendre function. Here's another one. I think this is known as the Hellinger entropy. And it's defined on, or its effective domain is a closed set, -1 to 1. Here is another example. It's like you might be familiar with this. Like in my experience, it has a few names, but I've seen it called like a negative generalized Shannon entropy. So if you remove this minus a and then multiply it by a negative, that'd be the traditional Shannon entropy. So this is another example of Legendre function. And lastly, I want to comment on this one, this negative log. This negative log is also a Legendre function. So Legendre functions are, a nice class, a nice family of functions, essentially. I also want to introduce this notion of convex conjugate. So if you have a function f that's convex and lower semi-continuous, we define its convex conjugate like this. You might have seen this called the Fenchel transform or the Legendre transform, in case you're familiar with that terminology. So the convex conjugate satisfies a really neat relationship, and it's this biconjugate relationship. So if you take the double convex conjugate, you get back just your original function. And we also have this really nice inequality, this Fenchel-Young inequality for all points A and B. And this just follows immediately from the definition of convex conjugate here. Okay, lastly, Legendre functions also satisfy a really beautiful duality property. So there's this theorem that goes back to Rockefeller in 67, which states that a function R is Legendre if and only if its convex conjugate R star is also Legendre. And in this case, its gradient is a continuous bijection with continuous inverse, which essentially means that its gradient is a topological isomorphism between the interior of the domain of R and the interior of the domain of R star. So this is a really nice property as well. Okay. And then we have this definition of Brecklin divergence. So if you have a Legendre function R, we define its Brecklin divergence to be the function dr, which takes in a point in the effective domain of R and its interior, and it's defined in this way. So straight from the definition, you can see that this term kind of resembles a first order Taylor expansion at B, and that's exactly right. So what the Brecklin divergence is doing is it's measuring the error between the value R of A and the first order Taylor expansion centered at B evaluated at A. And so Brecklin divergences satisfy these really nice properties. So first, the Brecklin divergence is non-negative everywhere. So this follows from the convexity of R and the subgradient inequality. There's this other nice property which states that if you have 2 points that are both in the interior of the effective domain, then the Brecklin divergence is 0 if and only if they're the same point. And lastly, Brecklin divergence is convex in the first argument, which means that if you fix the second argument B and you let A vary, then you get a function that's convex in A. And likewise, because of the strict convexity of the Legendre function R, it's strictly convex if restricted to the interior in both arguments. I also want to quickly comment that these first two properties seem to be like a hint that our Brecklin divergence is a metric. Generally speaking, it's not a metric because it's not symmetric. In fact, the only case where our Brecklin divergence is symmetric is when you take R to be the quadratic. So if you take R to be the quadratic, then dr of AB is equal to dr of BA. But that's the only case where that happens. So you can think of this Brecklin divergence as like a generalized notion of distance. So I also want to quickly show like a visual representation of a Brecklin divergence. So here we have our point A, and we're evaluating our point A at R, so we get R of A here. And here we have our point B evaluating at R of B. And so what I'm going to do is I'm going to construct a tangent line, so first order Taylor expansion, so at R of B. And then I'm going to evaluate this tangent line at A, and I get this point right here. And so the Brecklin divergence is just this distance right here you're measuring. So distance between R of A and then this error. And you can see that if I move my point A closer and closer to B, that this distance is going to shrink and shrink. So indeed, Brecklin divergences are measuring like a sort of generalized distance of the points A and B. So with that, we're ready to talk about the Brecklin proximal point method. So here's the context. So we have a function f that's proper, lower semi-continuous and convex. And then we have a set C that's non-empty, closed and convex. So C stands for constraints. So you should think of the C as like a constraint set. So if we want to solve this optimization problem, as in find a solution, X, what Brecklin proximal point does is it generates a sequence of points, xk, defined in this way, where dr is the Brecklin divergence and this alpha k is a sequence of positive real numbers. So it generates the sequence of points xk, and the hope is that the sequence of points xk converges to the minimizer of f for this problem, and also that f evaluated at these points xk converges to the minimum um, of f, right? So that's the hope with direct proximal point. And indeed, with very mild assumptions, you can guarantee that this sequence of points xk does converge to the true minimizer of this problem. So essentially what we're doing with this definition is we're taking our function f, and then we're adding this regularization term, dr over here. That's kind of regularizing our problem and hopefully making it easier to solve. And then that's how we're defining our sequence xk. Okay, great. Oh, I should also state that if anyone has any questions, please feel free to interrupt me. Okay. I want to highlight this connection with implicit gradient descent as well. So if we assume our f is differentiable, then we can, just use the standard first order optimality conditions in this problem. So if we take the derivative over here and then set our point, or set the resulting expression to be equal to 0, then we get this equation here, this equality. So we're trying to solve for xk plus 1. So rearranging, we're going to move this grad r xk plus 1 term to this side. And if we take r to be a quadratic, then the gradient is simply the identity. And so this simplifies to this equation here, and we recover the standard implicit gradient descent update. It's implicit because you have this xk plus 1 occurring on both sides. If we change this xk plus 1 to be an xk, then it would be the classical explicit gradient descent update. Something else I want to highlight is that in Bregman proximal point, one of the conditions you need for this sequence to actually converge to the minimizer is you need your sequence alpha k, you need the sum, the infinite sum of these alpha k's to diverge. You need it to be infinity, right? And notice that's trivially satisfied if I set alpha k to be constant. So if I set alpha k to be 1 for all k, then of course the sum is infinite. And even in that case, this sequence is well defined and will converge to the minimizer. So that's a bit of a difference between a gradient descent, is that we could set the alpha k's to be constant, and our Bregman proximal point algorithm converges just fine. Meanwhile, that's not exactly the case in gradient descent. Okay. So in traditional finite elements, we approximate solutions to problems of this form, right? Where E is some total potential energy functional, and V is some space of functions, and as before, C is a closed convex set that's encoding constraints, some sort of constraints. So we can extend Bregman proximal point in the finite dimensional case to solve problems in this setting, in function spaces. So in full generalization, Bregman proximal point for function spaces looks like this. This B is some bounded linear operator, and this gamma is a subset of the closure of our domain omega. We will not need this equality in full generalization, but we'll take a particular case for E and B and gamma later on. I also want to highlight that a bit of my work recently has been to justify the existence and well-posedness, essentially, of the resulting sequence UK plus 1 in the function space setting. So in finite dimensions, we know that Bregman proximal point works just fine. But in infinite dimensions and function spaces, there's still a bit more work to be done to really show that this sequence is well-defined. Yeah. Okay. So with all that mathematical background, we're ready to get into Signorini's problem. So first, we'll go over some standard definitions. So D is going to represent our dimension. So in particular, we'll take D to be 2 or 3, 3 dimensions later on. But you can talk about Signorini's problem in any dimension, really. So, and then our set omega is going to be a bounded Lifshitz domain, and we're going to partition the boundary of omega in this way. So we're going to have two sets, two complementary sets, gamma D and gamma T, that make up the boundary of omega. This D, later on we'll see, it stands for Dirichlet, as in like a Dirichlet boundary condition. And this T stands for traction. So this gamma T is where our traction forces are going to be occurring later on. So this epsilon denotes the symmetric gradient. This C will denote the symmetric positive definite uniformly bounded elasticity tensor. And so in particular, we'll see that sigma, which is C times epsilon. So that's why the C is needed and discussed here. So this gamma is going to denote the trace operator from H1 into L2. F is going to be an internal body force density. Phi is going to be a prescribed gap function, which is essentially going to measure the distance between our body and the contact plane. And this n tilde is going to be a prescribed unit vector field. So in particular, I believe in like the classical context, you take this n tilde to be actually exactly the outer unit normal. But for our purposes, actually, you could let it to be like just any unit vector field defined on gamma t, and it should work just fine. Okay, fantastic. Uh, Great. So let's get into Signorini's problem. So the Signorini problem models the deformation of a linear elastic body in the presence of a contact boundary constraint. So the problem is going to be posed on this space. So this space V of functions U and H1 with zero trace on gamma D. So my functions U, when restricted to the boundary on gamma D, I'm enforcing that to be zero. And our energy functional is defined in this way over this feasible set. And sorry, very quickly, I'm going to reshare my screen. Forgive me. I noticed that there's a small issue with my slides at the moment. So let me see if I can fix that. Okay. Forgive me, I wanted to reshare my screen really quickly. Okay. There we go. Apologies for that. Okay, many thanks. Yeah, so let's get back into it. So our constraint set is going to be this set K, where I'm enforcing the trace of U dot n tilde to be less than or equal to this phi. You can think of this condition as sort of capturing, like forcing our displacement. So U in this context measures the displacement of our linear elastic body. And this condition is kind of saying that our linear elastic body cannot penetrate the contact surface over here. So it has to come into contact, but it can't penetrate it on the traction boundary. So physically, it's about time we bring up a picture. So here, our linear elastic body is this orange like ball A. Its boundary is the boundary of A. And then the sigma is gamma t, so it's the part of the boundary that's coming into contact. So Signorini's problem is trying to answer what will be the equilibrium configuration of the orange elastic body resting on the blue rigid frictionless plane. And also, can we solve and find the exact displacement of our linear elastic body A? So we know it's well known now that there indeed exists a unique solution to this problem, but numerically what we want to do is we want to see if we can actually find that or approximate that solution. So I want to go over a quick overview of some numerical methods. So first, there are penalty methods. So essentially with a penalty method is you're encoding this constraint by adding another term to your energy functional. And you're essentially going to penalize your function if it doesn't satisfy this constraint. So the further away U is from satisfying this constraint, the more we're going to penalize that term. So the nice thing about penalty methods is that it introduces no additional variables, but when you keep iterating and keep refining your mesh, it requires large penalty parameters. And it can lead to non-physical penetration as well, since we're no longer enforcing that constraint exactly. So there's another popular method, which is Lagrange multipliers. The benefit of that is that it fulfills the constraint equation correctly and exactly. So you don't have this non-physical penetration occurring. But the con is that it introduces additional variables into your system. So now you have to track this extra Lagrange multiplier that you have to take care of into your system. So there's another method, interior point, which is really nice because interior point is a mesh independent algorithm. So that means as we keep refining, we won't need more and more iterations of our algorithm to converge to some error tolerance. And it can also be used to solve non-convex optimization problems, which is really nice. But one of the cons of interior point is that eventually, when you have to apply Newton's method to solve the resulting linear systems, those linear systems might be ill-conditioned when you try to implement interior point. So that's a bit of a disadvantage. So now with this overview, we can get into contact express our algorithm. So I want to discuss a connection first between our algorithm contact express and proximal Galerkin. So this method, proximal Galerkin, is an iterative method for solving certain constrained minimization problems, and it's based on the Brecken proximal point method that we saw just a bit ago. So ultimately, the first order optimality conditions for each Brecken proximal point subproblems amounts to this problem. So we want to find UK that satisfies this equality in the dual space. Again, for our purposes, we don't need the full generality of this problem, but I wanted to include it so that like we can see the connection with proximal Galerkin and Brecken proximal point. So what proximal Galerkin does is it defines this latent variable psi k in this way. And so using this, we can rewrite this equation as a system. So we want to find UK and psi k that satisfy this system of equations in the dual space. So when we take this equation or this system of equations and apply it in our case for Signorini's problem, we get the following system. So we want to find UK and psi k that satisfies this system of equalities here. And it's been shown that the solutions UK and psi k indeed converge to the true solution of Signorini's problem as you keep iterating. And I also want to highlight the notation I'm using here. So in this context, our Legendre function is just this generalized Shannon entropy that I discussed earlier, and we're shifting it by our gap function phi over here. And this, like all these parentheses, encode the like corresponding L2 inner product for each of these terms. Okay, fantastic. So with that, we can get into a formal derivation of contact express. So assuming sufficient regularity, we can apply integration by parts in reverse to obtain this equality here.
Oh, sorry, I have one question. Sorry.
Yes.
Do we still assume the n tilde is still an arbitrary unit vector on the surface, or if it should it be the normal vector on the surface?
Yeah, good question. So at this point, we're still assuming n tilde is just an arbitrary unit vector field on gamma t. But of course, you can totally think of n tilde as being the unit normal on gamma t.
Yeah.
So yeah.
So if I don't know what will happen in the future slides, but can we just assume like n tilde being a unit vector like 1, 0, 0 over all the boundary?
Yeah. Yeah,
Okay.
yeah, exactly. And actually later on, I'll take n tilde to be 0, 0, -1. So pointing down in the z direction. Yeah.
Got it. Thank you.
Yeah, thanks. Great. So if we apply the vanishing integral theorem to this equation, we get the strong form of, of our like underlying PDE here. So we know that this equation is true now in omega. Of course, I glossed over, we need to assume our UK, our function UK, is regular enough to actually do this. So if we substitute this expression into our first equation star in the proximal Galerkin system, we have this equation here. And since we know that negative divergence of sigma UK is equal to F, then these terms are going to cancel out. And so we're left with this equality here of the blue terms. Okay. So now I want to work on this term over here, the one all the way on the right over the boundary of omega. So since our function v has 0 trace on gamma d, and our function uk should satisfy this condition here. Essentially, what we're saying is that that the that the pressure is essentially parallel to n tilde on gamma t. Another way to think about it is that the traction forces in the tangential direction are zero. Yeah. So applying this first condition here gives us this. So we get rid of the boundary that's not gamma t here. And then applying this parallel condition over here gives us this. Okay. So thus, this equation that we had just a bit ago, we can rewrite this term, boundary term, in this way. And then the resulting equation enforces weakly this condition here, that psi k is equal to psi k minus 1 plus alpha k, and then times this pressure here on gamma t. Okay. So again, so this equation is kind of enforcing this weakly. And if we go back to our red equation here, if we test our PDE with a function v that has zero trace on gamma t as well, we get this equality here. Okay. So now using the second equation, this equation here, this second equation is enforcing this relation that we saw a bit ago, where we're essentially, like, this is how we define psi k, right? So it's enforcing that psi k is equal to this expression on gamma t. So ultimately, I can solve for this, like when I substitute this expression psi k into this equation here and solve for uk dot n tilde, I get this expression here occurring on gamma t. And now we have derived implicit contact express because we have a uk on the left-hand side and we have a uk on the right-hand side. But if we instead assert the explicit relation where we're taking this k and essentially lagging behind it, lagging it behind by 1 to get a k minus 1, we obtain explicit contact express. So algorithmically, our algorithm looks like this. So we have an initial solution guess u naught in v, and an unsummable sequence of step sizes alpha k. It's going to output an approximate solution u to C. Reading's problem. So we're going to initialize k to be 0, and we're going to solve the following problem, or I guess k to be 1 actually. So we want to find uk that satisfies this equation here, and satisfies this sort of Dirichlet boundary condition occurring on gamma t. Then we'll assign k to be k plus 1, and we'll continue solving this until a convergence test is satisfied. So this is explicit contact express written out. Okay. So in the case that we take n tilde to be 0, 0, minus 1, the explicit contact express boundary condition simplifies to this really nicely. So uk dot n tilde is simply going to be negative uk and like the third component of uk. But what if instead I take n tilde to be this vector here, right? So then uk dot n tilde is this expression here. So now the question becomes, how can we set each component of uk on gamma t to enforce the contact express boundary condition, right? So I have essentially I have too many degrees of freedom for this uk, right? There's many ways you can pick the components of uk to satisfy this boundary condition. All right, so how exactly can we choose uk to satisfy this in the general sense? And we can approach this by enforcing the contact express boundary condition in a weak sense. So I want to start by using a penalty method. So I'm going to, for sake of notation, I'm going to define g of u to be this. So this is the right-hand side of our contact express boundary condition. So letting kappa be a very large number, denote a penalty parameter, we want our function uk to satisfy this equality for all v and v. All right, so what are we saying here? So notice that these first two terms come from the PDE. So we want this to be 0. And what I've done here is I'm taking the difference of uk dot n tilde and g of uk minus 1. And I want this whole expression to be equal to 0. So the way you can think of it is like a balancing act, right? So I want this expression to be 0. So if I force kappa to be very large, like very, very large, then in order to compensate, this term in some sense should decrease, right? It should get closer and closer to zero because I want to enforce this equality. And so this is essentially what a penalty method does, and what I was mentioning earlier, is that this is how we're enforcing our contact boundary constraint weakly. So as before, as I mentioned earlier, some issues with this approach is that we need very large kappa to enforce this equality here on gamma t. And also, this equality doesn't use all of the given PDE information. So there's a bit of information we left out by just having this, right? So how can we fix these issues or improve our situation? So we're going to dive into a Nietzsche type approach, right? So the strong form of our problem is written in this way. So here's our PDE, here's our contact express boundary condition, and here's the parallel traction forces I was mentioning earlier in gamma t. So as we saw before, we can multiply the PDE by a test function and integrate by parts, and we get this equality here. Okay, so now I'm going to take this V right here, and I'm going to decompose it into its parallel part, or into the part parallel with n tilde, its projection onto n tilde, and then the orthogonal part here, right? So with this decomposition, we can rewrite this term, this V, in this way. And since sigma UKN is parallel to n tilde, essentially this orthogonal term is going to disappear. And so we're just left with the parallel term here. And so this is what it simplifies down to. So now what we do, just like in penalty, is we add a penalty term here, where kappa, again, is nearly a penalty parameter, but this time we're dividing by the mesh size h, right? So in a classical paper by Nietzsche, essentially he found that dividing by this h was better than just having kappa. So if you're encoding the size of your mesh into your PDE as well, that will help your method essentially. Okay. So we could stop here, but one of the things with this equality, if you notice, is that if I separate the equality into the bilinear form and the linear form, so if I move this GUK minus 1 v dot n tilde term to the right-hand side, then the bilinear form is going to be this term here, and then this integral with UK dot n tilde and v dot n tilde. And that bilinear form is non-symmetric, right? And it's non-symmetric because of this term here. Because of the symmetricity of sigma, I can swap UK and V here just fine, and that term is symmetric. And then same thing here, trivially, I can swap UK and V just fine, and that's symmetric. But that is no longer the case here. If I swap UK with V, it's ultimately non-symmetric, right? So we can very easily fix this by just adding a symmetricity term, right? So we're just going to add the term we need in order to make it symmetric to the left-hand side. So notice if I add this term to the left-hand side and then swap UK and V, that indeed the resulting bilinear form is symmetric. But of course, we can't just add this term to the left-hand side. We have to preserve the equality. So what you can do is you can then add this term over here, negative GUK minus 1, to the right-hand side. And so this ultimately yields the Nietzsche formulation here for all of V and V. So it's really nice to add this term to the right-hand side because, again, this is kind of enforcing the boundary conditions weakly. Notice if I add this term to the left-hand side and then factor out a negative of this term and this term, then ultimately what I'm going to get is I'm going to get UK dot n tilde minus G of UK minus 1. And so again, we get the boundary condition being enforced weakly. Yeah. So this sequence of arguments is known as a Nietzsche formulation for enforcing boundary conditions weakly. Okay. And this is actually how we enforce situations where n tilde is not just a really nice Euclidean vector, essentially. So in particular, we can take n tilde to be the unit normal on gamma t, and this is how we would solve for UK. Okay, great. So now finally, let's get into some numerical results. So I'm going to just set my proximate parameters alpha k to be 1 for all k, and I'm going to define omega to be the unit cube in R3. And the traction boundary, of course, will be the bottom face of the cube. And gamma d is just going to be the leftover part of the boundary. So I'm also going to take my forcing vector f to be like this, my n tilde to be this, my phi to be this. So remember, phi is measuring the distance between our body and some contact surface. So in particular, this represents the plane z equals negative 0.5. So we're measuring the distance between a point and the plane z equals negative 0.5, because that's where our cube is going to be coming into contact. And I'll take my initial iterate u0 to be this. Furthermore, I'll take sigma to be written in this way for Lamé parameters lambda mu, both 1. So this should be a little familiar. So in particular, such a sigma represents a compressible, homogeneous, and isotropic elastic body. And I want to highlight that the corresponding Young modulus and Poisson ratio for these Lamé parameters are 5/2 and 1/4, which apparently approximately match those of polystyrene and cast iron, respectively. I thought that was pretty neat. Yeah. So consider the case where we enforce zero displacement of our cube in the x and y components, right? So we're going to take our cube and we're going to force it down into a flat plane. And we're also going to make it so that our cube cannot displace in the x and y components. So one of the way you may think about this is that your cube is like trapped in a rectangular like cylinder, essentially. And so you're forcing your cube down this rectangular cylinder, and consequently, it's only going to compress in the z direction. Just after the slide, we'll see a figure of what I'm referring to. But because of this enforcement, our PDE simplifies really nicely. So we just have to solve this PDE, where U3 is like the z component of our displacement. And we can easily solve this for U3, and then ultimately we get our displacement U is in this form. So the reason why we want to investigate this is because now we have an explicit solution that we can use to test our algorithm, essentially. So this is what I was referring to earlier. So this black boundary here represents the initial configuration of our cube. And we're forcing our cube down this like cylindrical or this rectangular box. And it's only allowed to compress in the z direction. And so you can see this, you can see the compressing happening here. So notice that the bottom face of the cube has displaced by negative 0.5 units, which exactly matches what we expect, because it's going to be compressing into the plane z equals negative 0.5. Okay. So using our explicit solution for this problem, we can get the following error plot. So I use order 1 elements, Lagrange elements on a uniform mesh to obtain these plots. So I want to highlight this plot on the left first. So notice that each time we refine our mesh, the number of iterations we need to converge to some error tolerance doesn't increase, really. And so consequently, we can see numerical evidence that our algorithm is mesh independent, right? So if our method was mesh dependent, then the more we refine our mesh, the longer it would take our algorithm to converge to some error tolerance, right? But actually, it seems that we have the opposite here. So each time we refine, we have a lower and lower error tolerance, like by the time we reach iteration 7, which is really nice. And the second plot here is the true L2 error between our true solution and our approximate solution with contact express. So you can see that, or I should say, using this plot and using this data, you can compute the rate of convergence of contact express. So essentially, like O of h to the alpha, we're trying to find the alpha. you can use this plot to do that. And the L2 rate of convergence is approximately 2 as we expect, right? The reason why we expect this is because in the theory, we know that the L2 rate of convergence of your method should be one more than the order of the elements you're using. So here we're using order 1 elements, and so since 1 plus 1 equals 2, that's exactly why this is what we expect. And so our contact express algorithm is indeed matching this expected L2 rate of convergence, which is really nice. Here I have a few more simulations. So on the left, I have a ball in R3, and I'm compressing it. I'm forcing it down into, again, the plane z equals negative 0.5. And here I've cut the ball, the last iteration of our algorithm, in half so we can see really the displacement going on inside of our ball. And these simulations indeed are what we expect. On the right-hand side, I have a cube falling down or being forced down into this tilted plane over here. And indeed, both of these simulations appear to match our physical expectations. So we have introduced contact express, an implicit and explicit method for solving Noe-Reyes problem. So I want to discuss a bit of future work for this algorithm. So there's still a necessity for a rigorous analysis of contact express. So what I've given you is a formal derivation of how we can get it from proximal Galerkin, but the analysis is lacking, and so there's still a lot of more work that needs to be done to essentially like justify each step. I want to highlight that we have attempted to use mirror descent, which is very similar to a Breckman proximal point, to justify contact express, and there does appear to be a connection there, but again, there's still a bit more work to be done to justify that analysis. We'd also like to show Q-linear convergence with respect to iterations, at least for the lowest order discretizations. So that has still yet to be done. And lastly, we'd also like to try implementing contact express for a multi-body contact problem. So here we just have one body coming into contact with a plane, but we'd like to apply contact express where you have two bodies colliding together. Thank you.
Thank you, Noe, for your great talks. Does anyone has any questions? Well, I got one question. From my understanding, when you choose different Bregman geometries, it may give you different contact rules. And here you get your contact express. But when we think about other contact problem like the soft contact, do we need to choose another Bregman geometries instead of get the contact express?
Yeah, that's a really good question. So let me quickly go back to this slide over here, Grant. So generally speaking, your Legendre function should encode your constraint set, right? So here our constraint set is this inequality that we have here. And so ultimately the reason why this where is it? Over here. Why we chose this Legendre function is because, as we saw in like one of the earlier figures, the closer and closer you get to phi, the closer you get to 0, and then to the left of that, you're not defined, right? So essentially, this Legendre function is like encoding a greater than or equal to phi, and so that's why like this Legendre function was chosen, because we have this this inequality occurring here, right? But of course, in other contexts and in other scenarios, you might choose a different Legendre function. You might choose the Hellinger entropy we saw earlier, which is just like half of a circle essentially, or half of a sphere. That might be appropriate for certain problems, or maybe even the quadratic, which is a standard proximal point you might want to use for certain problems. So yeah, generally speaking, you should choose your Legendre function to encode this constraint set.
I see. Thank you so much. And also, I have a few general questions to ask. For the audience, if you have any questions, feel free to interrupt me. And for the first questions is from your experience, do you think that the applied math and the computational mechanics peoples will look at the same PDE problems from different angles?
Yeah, that's a good question. So, I don't have too much personal experience with those in computational mechanics, but I believe, like from the mathematical side at least, that I can say like certainly, like mathematicians would look at a PDE and really get down into the like deeply as to if there's a solution, when is there a solution, stuff like that. Uh, and I mean, I've experienced that firsthand. So like trying to justify like contact express uh, essentially and like how we can derive it certainly has been a challenge. And so like I'm thinking very analytically, seeing exactly what we need to get to this point. So yeah, I can say certainly that not mathematically, like math people will look at a PDE and try to figure out every single condition you need, not only for existence of the PDE, for example, but also for uniqueness. Yeah.
Yeah, and what do you think is the most challenging part in developing this work?
Yeah. So the most challenging part I'd say is certainly the analysis. Um, so we've done a bit of work trying to connect Content Express with mirror descent and trying to investigate like other derivations as well. But ultimately, our analysis hasn't been completed at the moment. So there's still a few gaps in that we need to address. Particularly, uh, one thing is this regularity part, right? So we can only do these manipulations if we assume our solution UK, our displacement UK, is regular enough, right? That we can do this integration by parts. Um, and like personally, I've searched through the literature to see conditions on when exactly you have that regularity, but for seniority's problem doesn't seem to be like a wealth of knowledge. So I would say certainly the analysis has been the like most challenging part for Contact Express. Yeah.
I see. Thank you so much. And you come from Bronx, how do you like your life in Bronx?
Yeah, so I can't speak for every department, but I can say with certainty that the applied math department is very collaborative and very supportive and very friendly as well. So there's always like a workshop or a seminar going on you can attend in like almost any field. And people are very open to discussing like their ideas, which is really nice. I also want to add that our department truly gives us like we the students like every tool we need to succeed in our work. And I'd also want to say that the professors are very friendly and helpful people as well. Yeah.
Is there any examples of tools that you need?
Yeah, I mean, something like, for example, like MATLAB, our department gives us, or actually, I think Brown in general gives students like a free MATLAB subscription, which is really nice. There's also like other subscriptions as well that you might need for your work as a student, like an Overleaf Pro subscription, which is really nice. But yeah.
Yeah, how about the computational resources like the HPC?
Yeah. We also have as students access to HPC. So I think you just have to create an account, and then you're essentially good to go for using HPC in your work. Like any student can use it as well. Yeah.
Thank you. And I really enjoy your talk, especially the way how you describe this problem is very clear to me. And I think you already do a good job with your research. Do you have any advice for students who want to work on numerical methods? Some skills or habits for them to develop when they start their PhD studies.
Yeah, certainly. So I would definitely encourage students to familiarize themselves with a programming language and to develop proficiency in it. So in the context of numerical methods, I know that Python and C++ have a number of numerical libraries. And so I would say like getting a good grasp of these languages can be very beneficial as a student. Of course, I also want to emphasize that having a solid understanding of mathematics is necessary at the end of the day, you know. And I would encourage students to learn the how and the why of what they're studying through math. So, yeah.
So for learning process, do you prefer to start to learn that from those AI tools, which will give you a very fast progress, or do you think it is still better to learn by yourself first and get some assistance from those AI tools?
Yeah, that's a really great question. So, in my experience, I find that simply because of the nature of, you know, of our work, that collaborating with AI isn't really going to produce any meaningful insight that you might gain like otherwise. So, like the deeper you go into your study, the more difficult it's going to be essentially to get a good response out of like an AI. So, I would say for like for your personal study or like for your theoretical work or something to I would say like just to work on your own because it's very likely that AI isn't going to provide you much help anyways. Yeah.
Thank you. So I have the same feelings these days. So for the audience, does anyone still has any questions?
Yeah, I do. Thank you very much. This talk was great, and I really appreciated how you walked us through the math at the beginning. Do you have any publications I can look at that deals with this work?
Yeah, unfortunately at the moment I don't have any publications, but I do have uh some slides on this work and then also some other work I'm doing that I can forward to you if you'd
Yeah,
like.
yeah, that would be wonderful. I work on contact as well, and this seems like a really effective way to approach it. So
Yeah. Thank
that
you.
sounds great. Thanks so much. I really appreciated the talk.
Hi, excuse me. Uh, a very nice talk. And I would just want to ask is, how is your method compared to the augmented Lagrangian method? Have you considered about
Oh
that?
yeah. Yeah, it's a good question. So we haven't corroborated our method with some of the popular methods like augmented Lagrangian. But I know that proximal Galerkin over here in this paper and also in another related paper, they matched their proximal Galerkin method with a number of popular numerical solvers out there, and I think augmented Lagrangian was one of them. So I could point you to their paper, but for my work in particular with this algorithm, we haven't uh, like compared it to augmented Lagrangian.
Okay, okay, I got it. And another question is that how do you think your method, current framework can be generalized to maybe a larger system containing multi-body like contact? How
Yeah, great
efficient
question.
is that? Yeah, I think.
Yeah, so I want to comment that one of the fallbacks with Contact Express is what's going on here. So
Hmm.
when you lag behind this UK to be UK minus one, you're essentially losing a bit of your approximation power, right? And so like you no longer you have like less exactness. And so I would say if we wanted to apply Contact Express in this broader context of problems of contact problems, that we might want to use something that looks like this. So we might want to use implicit contact express for those situations so that we have hopefully like a better approximation there. Yeah.
Okay, okay, I got it. Thank you.
I know it. Do you mind to share your emails in the message? So maybe you can continue to share your slides or the forward the more information.
Yeah, of course. Let me share that right now. So there's my email there, and I can also share my slides. Let me do that. There we go.
Thank you so much. And this talk will be recorded and later uploaded in our YouTube channels.
Yeah, awesome. Yeah, I'm looking forward to seeing it again. Thank you.
Yeah. And thanks for your great talk. We will later send you a gift. And please send your address to my phone numbers. I will send it to you later.
Great. Sounds good.